represented my work fairly. Well,
now this paper was written in 2005 by a satellite nerd named Pinker. He is wholly unconcerned with the global warming debate. It's as though he lives on another planet. He lives for verifying whether satellites are doing their job. That's what Pinker is all about.
So the answer is Pinker's just not interested in that question. Doesn't care. So that was also a surprise to me. I mean, okay, maybe that person's completely out of it. So I thought I'd contact Dr. Pinker. And the first thing I noticed was she's a woman. And I asked her, well, who's right, IPCC or Monckton?
The CO2 radiative forcing value that Mr. Christopher Monckton is quoting refers to the impact on the Earth's radiative balance. The numbers that we quote in our paper represent the change in surface shortwave radiation due to changes in the atmosphere, clouds, water vapor, aerosols. These two numbers cannot be compared at their face value. To the best of my understanding, this is the source of the misunderstanding. Our work was properly interpreted in the latest IPCC report.
And Professor Pinker was good enough to send me a detailed description of exactly where Lord Monckton went wrong in his interpretation of her work. And I'll put up the whole document up at my website so anyone can read it, but here's a summary. Clouds have two effects on radiative forcing. There's two things you've got to worry about. Remember when we talked about what radiative forcing was? It was the difference between the short-wave radiation coming in and the long-wave radiation coming out. So on the left, you can see what they do to the short-wave radiation, the radiation coming in, and that is they block some of it. They reflect some of it back into space. Some of it gets through the clouds, but they have the effect of reducing short-wave radiation coming in. The other thing they do is shown on the right, though, and that's they also block long-wave radiation. The radiation that's coming up from the Earth, in the yellow arrows there, goes up, it bangs into the clouds, they absorb that, it warms up the clouds, they radiate it out again. Some of it radiates back out to space, some of it radiates back to the Earth. So the effect is they block some of the long-wave radiation. So they affect both sides of the radiative forcing equation, and Lord Monckton's mistake was that he only looked at short-wave radiation. He didn't consider the effects of clouds on long-wave radiation. And as I said, Professor Pinker went into details of that in her explanation to me, and you can read that on the web. But I also find that I do agree with Lord Monckton about doing a calculation like this. It's a good way to work out what sensitivity is. So, but what you want to do if you want to do that calculation is you want to compare our climate with a climate that's very, very different. That gives you a much more accurate idea of what forcing is, because if there's a big difference and it's done over a long period of time, remember sensitivity is defined as the long-term change, you get a good handle on it. So I want to tell you about the last ice age. Climate then was very, very different. We had these huge ice sheets that covered lots of North America and Europe and Asia. Snow lines were lower. It was colder, and how much colder depended on where you were. Glaciers were 5 degrees colder. The sea surface was 3 degrees colder. Up in Greenland, it was, 20 degrees colder. And the vegetation was different too. Instead of having forests that we have today, those forests were replaced by open grassland. And also, there was more dust in the atmosphere, and that was because there was less rain and the deserts were bigger and they'd blow more dust up into the air. And there was also less CO2 in the atmosphere. So we can combine all that information, which came from that book right there, Ian Plimer's Heaven and Earth, to work out the sensitivity. So same calculation as before, we're going to look at the change in temperature divided by the forcing. So how much cooler was it during the last ice age? 6 degrees, that's the number on the top of the equation. What about the forcing? Well, there were a bunch of things then we noticed about the climate then. There was less CO2, that makes about 3 watts per square metre. There were these big ice sheets, they reflect sunlight back, that cools the Earth. It's a big effect. It's as strong as the amount of having less CO2 in the atmosphere at that time, 3 watts per square metre. 2 smaller effects. The dust caused some cooling, about 1 watt per square metre. And the change in vegetation. Instead of having forests which are kind of dark, we had grasslands which are kind of light. So the forest absorbed more sunlight than the grassland, so that effect was to produce some cooling. So you do that calculation, divide 6 by 3 plus 3 plus 1 plus 1, that's 6 over 8, 0.75. Everyone can check my working here, and we get that as the sensitivity. So let's correct his calculation. Instead of 0.12 for sensitivity, a correct answer or a better answer is 0.75. Now, instead of 0.43, the answer is if you double CO2, you're going to get about 2.8 degrees of warming, and we can compare that with the IPCC number, which is between 2 and 4.5. That's why global warming is a problem, and that's why the question in this debate should be resolved in my favour. Thank you.
Now, thank you, Dr. Lambert. Now, if you stay on your feet, and Dr. Monckton gets the opportunity to ask you a question.
Okay, I'll start here.
That's right. It. You stay up there. And
what I'd like to do is to look at your calculation to do with the last ice age and take you back, if I may, to a previous ice age, 750 million years ago. A mile of ice at the equator, ice planet all round, therefore, at the surface, 300,000 parts per million of CO2. Will you tell me how that much CO2 could have been in the atmosphere and yet allowed that amount of ice at the equator?
In order to do that correctly, you have to do a calculation like this. So we had a forcing from CO2 at that time, which was a warming, but we also had a forcing from the ice sheets. In this case, with much smaller ice sheets, we had 3 watts of cooling. If we have ice sheets that are actually covering most of the planet, you have a huge amount of cooling effect from all that ice. Unless you actually do a calculation like this one, you really can't get a handle on the sensitivity. So if we want to try to work through the actual numbers and see where it comes out to, but the reason is, yes, you had a warming from the CO2, but you have absolutely massive cooling from a huge ice sheet. And also, I believe at that time, the sun was a bit cooler as well, so there's another forcing to consider, the change in solar output.
Right, well, a good moderator doesn't do anything other than control the debate, so I won't ask a supplementary question, but it is time for Dr. Lambert to ask Lord Monckton a question.
Okay, I just wanted to ask you about your calculation. I checked with Professor Pinker, and she says quite clearly that you're wrong, and we can go through, and obviously I don't expect you to say, oh, I got it wrong, without having a look at her work, but what steps will you take that if you look at her correction of what you did and decide that, oh, I've made a mistake, how will you correct the record? You've been putting up this calculation all over the place, and I think you've really, really got it wrong badly.
Right. Well, the first thing to do is obviously I will be checking with Professor Pinker.
Of course.
And I will be checking once again the documents of the IPCC, and I'm very intrigued that she thinks they represent her correctly, because their conclusion is to do with high clouds, whereas her conclusion is to do with low clouds. And there's a clear mismatch there. But let me have a look at 1 or 2 other areas in which we can establish low climate sensitivity. We're going to verify this by looking at some other results. First of all, the oceans have been cooling over the last 6 years because we have reliable, for the first time, methods of measuring the climate-relevant surface layer of the ocean using the Argo bathythermograph buoys. There is the graph produced by the Argo team of the last 6 years. That shows ocean cooling. Now, one of the fundamental and generally agreed points on both sides in this debate is that the oceans would have to be accumulating heat energy if the imbalance to which you referred earlier existed. Yet we have that cooling. All right, it's only 6 years that we have really good measurements. However, a recent analysis by Douglas and Knox, 2009, re-evaluating all the data going back something like 68 years, finds no net accumulation of heat energy in the oceans at all over that period,